Welcome everyone. Let's see, there we go. Okay, yeah, so welcome everyone to this Wales and Western branch webinar titled Data in the Water Industry. My name is David Christensen. I am the Wales and West Chair for this branch. Today we have three speakers. We have Edmund Willets from Wessex Water, Cillian Kerr from Welsh Water, and Lynn Bushy from Createch Solutions. The idea behind it is have general topics covering general things regarding data in the water industry. So there's no specific theme, just as long as they're covering data. But two of the speakers are from client side, so water companies, and then we have the third speaker more from the contractor side. With questions, we're going to have those at the end of the webinar, so if you could all just write your questions in the Teams chat function, that would be fantastic. And then I will read those out to the panel of speakers at the end. And yeah, for any questions, or if you're interested in getting involved with the Pipeline Industries Guild, either the Wales West branch specifically or any other branch across the UK, then you can either get in touch with me, you can see my email there below, or you can go to our website, just Google Pipeline Industries Guild, and there's also plenty of URLs throughout this presentation. Also, do please note that this presentation is being recorded and is going to be posted to our YouTube channel later on, probably either next week or the week afterwards, and it will be in various socials, mostly on LinkedIn. Okay, great. On that note, I will stop presenting and hand over to our first speaker, Edmund Willets. So please, Ed.
Hi there. Yep, I'll just get my presentation up and right. Can you all see that?
It's working for me. Thank you.
Great. Okay. Well, so now I was to get it working for me on my screens. Bear with me one moment. Sorry. So too many screens open in front of my face. Right, never mind. I'll crack on. So my name is Edmund Willets. I'm Ed Willets. I work on an asset reliability engineer for Wessex Water, and I work and I'm going to speak to you about what we're doing to use Storm Harvester to help us move to more condition-based maintenance. As a quick run through about what I'm going to cover. I'll start off with some background about basically the network, what's actually physically going on. Then I'll move on to what's our problem, what's the challenge we're trying to solve. Then how Storm Harvester works, Storm Harvester program and a company. Then into the results, does it work? And then further move into how we're looking to expand the work we're doing in terms of doing our monitoring and also the condition-based maintenance approach. So start off with why do we need storm overflows? What they are is basically they're relief valves for our wastewater system, for our sewage system. And hopefully this diagram you can see you've got a house and you've got industrial buildings, and they're normally putting they're discharging sort of foul waste into our sewage system, and that will flow down here to the water recycling centre or sewage treatment works, you might call it. However, in wet weather, what will go and happen is that we'll have rain runoff from roofs and from the roads, and that will also go in and fill it in the sewer. And hopefully, most of that should also merrily flow off down to the water recycling centres. But if there's too much coming in, then we'll go and sort of fill up all the capacity of our sewers, and they have to go somewhere else. And so we'll discharge them to permitted locations, which usually be sort of the sea or a river or a brook or potentially a wetland, like a rebed wetland for treatment. And so the reason we do that is because if we didn't, it'd go, if we had the system over capacity, got surcharged, it'd have to come out at the weakest point, which would probably be someone's toilet. And then we have a customer problem, we've got a public health issue. So that's roughly how the system works and why the storm overflows are there to start with. And then we'll go into, I thought it'd be important to actually address why this gets into the news today, rather than just try and avoid it. And basically how this links in is that we're using storm halves to use our data that we feed it with our storm overflow information. And so that's why this is relevant. So I'm sure you'll be more than aware of all the stories that have been in the papers and the press for the past few years. And you might have, certainly I've read comments about water companies dumping or spewing sewage into the seas or rivers. So lots of negative stories out there, but that's not actually it's misrepresentative, because we're not actually discharging sort of a thick brown liquor into rivers or the sea. In wet weather, primarily what's going out to discharge is rainwater, because we're filling our sewer capacity up with a whole lot of rainwater, storm flows, and therefore what is also going out is then rainwater. But it's not just rainwater, because much like if you say got a bottle of Coke, drank most of it, and some dregs left at the bottom, if you then fill that with tap water, you wouldn't still have perfectly clear tap water left. It would be slightly dirty. In a similar way, if we go and fill our sewers with storm water, what comes out from our storm overflows is going to pick up, some of the foul waste in there too. But simply, the major concerns about the storm overflow operation is down to water quality, but simply stopping all the storm overflow operations today, tomorrow, this week wouldn't necessarily have that big an impact on water quality. There's still work going on in this, but think about sensibly. If what's going into the sewers is storm water, and what's flowing out storm overflows is also rainwater, then the extra rainwater in rivers and the sea is not going to make that much difference to water quality. But and therefore, if it's not our storm overflows causing the problems, then we need to look elsewhere. Is there an industrial polluter upstream? Is actually sort of runoff from sort of agriculture and from the fields? And actually, we want to go and really solve this problem. It's going to require legal and planning changes, because at the moment, if you want to go and have a new housing estate going up, that doesn't need to take into account about whether there's actually extra capacity in the sewage system to be able to cope with that. So therefore, any original capacity that there was at design and build may have already gone, and that's why there might be so many storm overflows. And similarly, the developers don't necessarily need to keep their foul and storm the foul and surface water separate. So that's a bit of background about what storm overflows are, and I want now on to basically what we go and do about monitoring that and how we use that data and how we're using that differently. So quick little bit about terminology. I'll try not to use any jargon. However, if I do, some bits might crop up. EDM is event duration monitoring. It's storm overflow monitoring. CSOs, that's combined sewer overflow, foul and surface water. An SBS is a sewage pumping station, and a rising main is a pressurised, especially pressurised sewage pipe. Now, our current problem is that this is actually a graph from last year, but when we were first really trying to install our storm overflow monitors at scale, we had about 1,000 alarms coming in per month. About 2 years later, that's up to about 3,000 alarms per month. Last year, it's about 5,000 alarms per month. Now it's between about 5,000 and 6,000 alarms per month. That basically, you've got too many alarms coming in, and we can't deal with that. It's just too many to manually handle. So if there's too many alarms, we're going to miss the real issues. If we miss the real issues, then we have the impacts we don't want. That's when we can impact the customers. That's when we can impact the environment, and it's the stuff that happens we don't want to. Also, I should point out, related to the previous slide, I've said about storm overflows happening. It's mainly rainwater. If overflows happen in dry weather, potentially there is water companies aren't always in the clean, in the clear here. So pollutions do happen, and they are prosecutable. So I'm not claiming that nothing ever goes wrong anywhere. So as you can see, some more recent numbers from November, December and January. You can see, look, 26,000 alarms a month, 21,000, 26,000. It backs up the previous picture. There's too much data for us to deal with. And so therefore, we needed a way in Wessex Water of being able to handle all this information coming in and actually be able to do something with it and then achieve better outcomes for everyone and for the environment. So after doing some trials of different companies and different systems, we opted to buy and use a product called Storm Harvester. And what Storm Harvester does, we go and give it, we've sort of sent them 2 years worth of historical data from level data for sort of looking at sewer depths and sort of tank depths and things like that. They learn what normal look like by comparing it with rainfall, and then we feed it information on a daily basis, and they go and tell us whether things are okay or not. So on this chart here, you can see this brownish line. That's the sewer level. So that's from a sewer or a tank or a pump well, something like that. The blue is the rainfall, and then hopefully you can make out this dashed line going in grey. And you can see it's normally sort of down here, but when the rain comes in, it gets stretched up. And this is our operating envelope. It's just like colouring in a picture. If everything stays in the lines, that's good. That's healthy. We don't need to worry about anything. If the brown line goes outside the dotted lines, then there is a problem. Then there's a potential issue, and that's where I want to investigate, see what's going on. And in this example here, it all stays within the lines, apart from this slight bit over here, where it goes outside. But even this one, we won't be so fussed about because it's just after rainfall and it just strays out slightly. So it might be, the timings and the model's slightly out. So that's basically a nice healthy picture of this one. And yeah, so Storm Harvester is working by it's detecting unexpected behaviour. If it's expected, who cares? Do nothing. Unexpected, that's when we go and act. And as I said, it's adapting what's normal and with comparing that rainfall to tell us what should be happening that given day for a given amount of rainfall. And the expected behaviour that we don't care about, that we expect Storm Harvester to say not to tell us about, be high levels during rainfall. So it tips down, more rainfall goes into a sewer, levels go up, fine, if it stays with normal bounds. There's objects in a chamber, like structurally, like step irons, metal rungs in there, or else if we've got sort of, the structures, if that's just how that's the monitored, chamber, fine, don't tell us. Similarly, as maintenance work or alarm tests going on, don't care about those, please don't tell us. However, what we do want to know about, we've got blockages. If we've got low levels, which should be an upstream blockage probably, or whether we've had a spill, a storm overflow happening, an overflow event happening without enough rain. So again, that would be there's not enough rain to cause an overflow to happen. So therefore, there's a blockage or something else going wrong. Now on to some results. So does it work? Simple answer, yes. A few examples. So this one, you can see the sewer levels bounced up and down. It starts really going outside the normal here, and then something happens. What happens? An operator went to site and removed this whole bucket full of rag there and cleared a blockage. In case you're wondering why it took so long to pick up this fault, is because actually this site only went live on the Storm Harvester system the day before, so it actually picks it up on the first day it could. Similarly, this site was working fine, normal down the bottom, then shot high, didn't get to this red zone here, which should be actually an overflow, a pollution at this site. So it didn't pollute, but then went down. What happened? An operator went to site, found a load of fat and a plastic bag causing a blockage, removed that, and then it went back to normal, as you can see here. And one slightly different one, normal, staying within the these grey operating envelope, but then drop below it. So what's happened? They went back up. What happened? An operator went to site and found an upstream blockage that was caused by all this grit and this silt. Remove that, and they went back to normal. So that's what we're looking to go and do. We're looking to go and catch these problems before they go and have an impact on anyone, before they cause a pollution, before they harm the environment, before they cause customers any bother. And the types of things we're picking up blockages that's causing sort of a full overflow, siltation, so a slow blockage building up over time. The post-rainfall partial blockages, this one's really a highlight because these are the ones we're probably the most important to pick up and the most useful for us. That's when it's absolutely tipped it down outside and we've washed into the sewers all the grit and the leaves and the mud, and then after the rain's dropped off, the flow's dropped off, some of that gets left behind and forms a small blockage, like a small weir or a small dam in our sewers, and then starts to catch more material. So that is the start of the next blockage, the start of our next pollution. So if I identify those early and keeps our sewer pipes running freely, then we're not going to have a pollution there. We're not going to have problems, which is really what we're aiming for. We can also pick up unhealthy sensors, so the data's just done something suddenly unexpected, that's really helpful for just maintaining our assets, really making sure our telemetry system is working correctly, and also things like broken pumps, which again we'll see with can identify with changes in levels, things been unexpected. So that's what we've been doing with storm harvest to date, and on the back of the successes we've all been having, I should mention actually we started trialing the system back in 2020 as part of a trial of 3 companies, and we've been adding sites in earnest since last January. And what we're now looking to do, now we've realised we are having successes as we expect them to be, we want to expand our number of monitors out there, so amount of data we can feed into the system. So to date there we've got about 1,200 signals in Storm Harvester, and we'll be increasing that up until summer, something close to about sort of over 1,500, probably between 1,500 and 1,800. However, and that'll be all the signals we've got for our regulatory storm overflow monitoring equipment. After that, we want to be installing additional monitors out there in our network, so more physical kit out in our network. And we've a group of us did some work back in last year, and we think there's probably about next 3,500 sites. We think they're our top priority ones, and they can shown here in a nice multicoloured map of our area, put together by my placement student Michael. And yeah, but you don't need to worry about basically all the dots, all the shapes, that's a monitor. And we decided this 3,500 by looking at sort of potentially high risk assets, so assets we thought were more likely to have blockages forming at, like siphons and tanks and flow control devices. And also where we've had historical pollutions, so high risk of pollutions, and also sort of catchment coverage. So where we want to go and where we think part of our network is underserved with monitors, we'll add extra ones in there just to go and bolster the visibility of issues. Now, already on this, you might be able to see there are some gaps in this, but they're mainly geographic. This hole here is it's the Mendip Hills. This is Salisbury Plain. I think that's Cranbourne Chase, and so that's just there aren't people, or there aren't also there's not a waste network there. But all this is feeding into a larger shift into a condition-based maintenance approach. At the moment, we're more reactive, more mixture of reactive and scheduled maintenance. So we're fixing a problem, waiting for something to go wrong. We get an alarm when something's going wrong, and we're reacting that to fix it. What we want to shift to is condition-based maintenance, basically go from fixed problem to keep the system healthy. And because if we can have systems like storm halves that tell us when things are just drifting from normal, are starting to act unexpectedly, then we can intervene early before it has any impact on the environment or our customers, or cause major failures. We can do nice planned slow time interventions without rushing around and any of the panic or adverse effects. And that's really what we're trying to do. Nice early intervention by early identification of problems. This isn't just using Storm Harvester. We're also using other tools, and we're still developing more. We've got a rising main burst detection system, basically using a bit of mass balance. So we're putting, we're looking at how much what flows are entering rising mains, and we're looking at what's leaving it. And if there's a difference between the two, we're looking for leaks. See where's it gone. Pump performance, again looking at pump output flows and whether they're doing what we expect them to be doing. But as a whole, we're looking at changes of behaviour. If something's changed, that's just something's going wrong, and that's where we want to go and intervene. And so with all of this, we've got a lot of data out there at the moment. We're looking for new systems to make better use of it, to inform our decision making and basically have more timely intervention. And yeah, that's the end of my presentation, and I hope that's been useful for everyone.
Thank you very much, Ed. That is really interesting. I'm sure there'll be plenty of questions towards the end. Next along, we have our next presenter, Keely Anker from Welsh Water. Keely, I'll hand over to you.
Thank you very much. And yeah, thank you very much for that, Ed. It was really interesting. I even learned a lot too. So yeah, hi everyone, I'm Cillian Kerr and I work for Dŵr Cymru Welsh Water and I'm an energy analyst. So since June 2020, I've been working on Welsh Water's net zero work package for process emissions, and today I'll be discussing what process emissions are and how data will be vital in the race to achieve net zero. So for those of you not aware, at Dŵr Cymru Welsh Water, we are committed to reducing our total greenhouse gas emissions by 90% by 2030 and achieving net zero by 2040. So by net zero, we mean that the amount of greenhouse gases that we release into the atmosphere is equal to the amount of greenhouse gases that we remove from the atmosphere. So specific to me in this presentation, I'm working on work package 4 of our net zero plan, which is working towards reducing our process emissions by 50% by 2030. So in the process of treating wastewater, which is what you'll see in the video just on the right, greenhouse gases are emitted, which we refer to as fugitive or process emissions. So these emissions are mainly methane, CH4, and nitrous oxide, N2O. So both gases are of noticeable concern due to their high global warming potentials. So they're 28 to 36 times and 365 to 298 times respectively. So the global warming potential is a measure of how much energy the emissions of a gas will absorb. So the larger the global warming potential, the more the gas will warm the Earth compared to CO2 over the same time period, and that time period is usually around 100 years. Today in this presentation, I'm solely focusing on N2O. So how is N2O produced? Well, to answer this, we need to first understand the wastewater treatment process, as well as nitrification and denitrification. So wastewater is generally treated in one of two methods, either through filter beds or aeration. So for this presentation, I'm focusing on the aeration method. So put simply, air is pumped from the bottom of the aeration tank containing wastewater and bacteria, and then this keeps the bacteria supplied with oxygen and they multiply and digest the impurities within the sewage. So in the images, I've sort of given what a standard aeration system might look like, and this is a close-up of the diffusers. So simply air is pumped through them and aerates the water like the video show. So focusing on nitrification, this is the sequential conversion of ammonia to nitrate and ultimately nitrite to nitrate, and it plays an important role in the biological water purification of wastewater. Ammonia in wastewater could originate from a variety of sources, including proteins from blood, urea, cleaning chemicals containing ammonium compounds, and so on. In an activated sludge system or other biological treatment system, nitrification occurs under aerobic conditions. So nitrification, which is shown within the green circle, is a biochemical reaction that occurs inside bacteria. And there are two types of bacteria. These bacteria are collectively known as nitrifiers and are atrophic, so i.e. they get their carbon source from inorganic carbon or carbon dioxide. In a biological water treatment, denitrification is generally the next step following nitrification, and that's shown in the blue circle. Here, nitrate and nitrite are transformed into nitrogen. The gaseous nitrogen escapes out of the water into the air, and air exists for 78% out of nitrogen and 21% oxygen. So nitrogen is absolutely not polluting the atmosphere. It's what we need. In completion of either of these two processes, that can result in N2O gas, as conversion to nitrogen gas does not take place. So these are some examples that can impact the completion of this cycle. So the main conditions triggering N2O production and emissions from wastewater are as follows: low DO, so that's dissolved oxygen, and that's anywhere between 1 to 0.5 micrograms a litre of oxygen during nitrification, and high dissolved oxygen concentration, so that's above 0.05 during denitrification. Nitrogen oxide accumulation during both nitrification and denitrification, extensive aeration leading to stripping of N2O from the liquid phase to the gaseous phase, so that's just too much air being pumped into the wastewater, limited organic carbon for denitrification. In addition, temporary conditions such as anoxic aerobic cycling, so that's no air, or fluctuations in substrate concentrations such as peaks of ammonium due to temporary loading, so that might be a treatment system putting in too much ammonia, so for example, a laundrette nearby, and that can also lead to increased N2O emissions. So the production pathways of N2O and wastewater treatment are highly complex, regardless of how a wastewater treatment works performs, nitrification and or denitrification. There will always be potential for N2O to be reduced and emitted due to the complex metabolic mechanisms involved in its productions. Treatment processes that emit lower levels of N2O have been associated with high process performance and greater extent of total nitrogen removal. Thus, it is possible to reduce N2O emissions along with improving process performance and meeting compliance. And just for reference, dissolved oxygen, what I mentioned, is a measure of how much oxygen is dissolved in the water. So the amount of oxygen available to living aquatic organisms. So just for some more background, so UK Water Industry Research, or also known as UCWEAR, developed a standardised workbook for estimated operational greenhouse gas emissions known as the Carbon Accounting Workbook. So this brings a consistency and accuracy to the reporting process across the water industry. The workbook has been in place for over 10 years and is updated annually to reflect the needs of the industry, including changes in carbon accounting practices. In 2020, the N2O emission was adjusted by a factor of 2 in the workbook version 15, which increased the total carbon footprint. Following completion on the research work currently being undertaken in the water industry and measurement trials that are currently being carried out by ourselves at Welsh Water, it's expected that the reported footprint will increase by a further 50,000 tonnes per year. So the water industry, as I said, it's been reporting underneath, but this sort of gives you a context of what that equates to. So basically 0.9 million average annual car emissions. And for context, the location-based accounting method represents the carbon footprint taken at the average emissions intensity of grids on which energy consumption occurs, where we have a market-based method which reflects emissions from electricity and natural gases that companies have purposely chosen. As such, the market-based method reflects the emissions from the electricity and biomethane that a company is purchasing, which may be different from the electricity that is generated locally. So in relation to the work that we're carrying out at Welsh Water, we have currently looking at 6 of our wastewater treatment works with a minimum of 4 weeks of sampling. We've got 2 Unisense liquid phase probes installed in either one or multiple aeration lanes, and that creates a risk-based model and generated N2O emissions for the site utilising the site process data. And I'll touch on how long we've actually been monitoring in the next slide as well. So to date, we have been working on 4 of our sites. With the next couple of weeks, we'll be moving to our final 2. So as you can see on the dates, and we have our emission factors also present. So some of our key findings. So a Cogmores, which if I go back is displayed here. It's a conventional aeration activated sludge plant. So the site suffers from low DO, so majority of nitrous oxide is associated with low DO risk. There's clear opportunity to lower risk and N2O emissions by increasing the DO. We had a diffuser replacement, which in the next couple of slides I'll show you the impact, but that improved DO resulting in lower N2O production and an estimated reduction of 47% if all lanes and zones have diffuser replacements. And we've actually come back to that site for further testing now that we've completed our blower and diffuser replacement. Risk varies from lane to lane and zone to zone, so we cannot assume that there's the same emissions across all of the lanes. So we have been testing on multiple lanes and multiple locations within those lanes within this further analysis that we're carrying out. So our key findings is that lane 1 was undergoing diffuser change during trial period to replace old and broken diffusers. Impact of returning to service of lane 1 seen across other lanes with improvement in DO. So basically, whenever we brought that lane back online, we seen an automatic increase in DO across the other lanes without actually having to change those diffusers at that point. Less losses through the system from the new diffusers in lane 1, and that's why it's improved. Evidence that better, more stable DO control is key to minimising N2O production, and there's still work, as I mentioned, to be done on site, and we have some control software to improve the variation in DO, but initial results are promising. So here we can see that whenever we'd replaced the lane 1 and brought it back online, that we had an increase in DO. So before the 25th of May, we had 186 tonnes of CO2 equivalent per year, and after, whenever they came back online, it was an estimated 35 tonnes of CO2 a year. Some of our other key findings were that there's a strong seasonal variation, so that's consistent with existing literature, and you can see the difference between a summer emission and a winter emission. And this shows our temperature history across one of our sites. And we also have aeration control. So early results show at our Pennebont site has a low N2O emission, and this is backed up by fellow consultants, and aeration control, which I think Lynn might be touching on, so I'll not go into too much detail, but essentially it's a system that you integrate within your aeration system to make sure that your blowers are running efficiently to treat the wastewater. So to summarise, how is data helping Welsh Water's journey to 50% process emission reduction? So it's playing a vital role. It's helping us improve our understanding of N2O emissions with accurately modelled and real-time data, particularly when compared to the theoretical values currently used to estimate emissions. It's allowed us to financially plan for mitigation and monitoring strategies in PR24, using the learning from the Cobalt Water solution to cost for a much more affordable monitoring campaign than the conventional monitoring approach would require. It's improved our understanding on nitrous oxide emissions across several asset types by using real-time monitoring technologies and developing advanced learning models, and it's helped us understand what improvements can and should be made for our processes to reduce nitrous oxide emissions and demonstrate the use of process changes for emissions reductions. And thank you all for listening.
Thank you very much, Keely. Oh, very on time there. Bang on 15 minutes, pretty much. That's great. Okay. Finally, then, I will hand over to Lynn for her presentation, and then we'll go to questions at the end after that. All right, Lynn, all yours.
Yep. Let me put up the presentation. Can you see that?
Yeah,
I can see it.
Excellent. Hi, I'm Lynn Bouchy. I'm a product line manager for Createch Solutions. So as David said, we're on the vendor side and we especially focus on process control solutions and specifically in the water industry. Okay. Slides are not moving along. Sorry, do it this way. There you go. A couple of things about us, because that's important to understand how and what we do. So we're a small company based in Spain, and as I said, we do process control, and our team is comprised of mainly process engineers, IT engineers, and that's really the essence of how we do things. We have a process team who defines a rationale, a control philosophy, and then the IT team will implement that to a particular application. We really focus on the digital side of things and the control, so irrespective of whatever specificity of the application, whatever instrument brands there might be and things like that, and that's why we've got a wide range of applications of different sites across the world. So the way we implement this and how we manage the data to be able to do so is can vary site by site, but this is a general idea of how we would usually implement the solution. So we use a PC server. That's what would be shown here in the middle with the Create Pro computer. That PC server is located on the site where we are controlling some processes, and it communicates with the site PLC. What this means is that it reads the data it needs, key signals for the control via the PLC, and then it will send back through to the PLC orders to whatever equipment it will be controlling. And therefore, with it being on site, the data remains on the boundary of the site. So your data's on site, your control's on site, and so this is very relevant in terms of cybersecurity. This architecture also enables a security in terms of process control continuity, because we don't overwrite whatever pre-existing control system there was. It will sit so alongside whatever was pre-existing, so that if you ever lose that communication between PLC's PC, then automatically it'll just revert back to whatever was pre-existing. In some occasions, we do access this remotely, commissioning, upgrading, service support. And when we do so, obviously in compliance with IT policies and rules of the particular site and client. And also what we access is specifically the PC server where the solution is implemented. So this is all to enable a very high level of both cyber and process security, of course. It was very relevant discussions in this respect. Now, what we offer as a solution really has two parts to it, and the value of the data has those two parts. So this is the first one, the process intelligence, and this is more linked to the HMI really. So dashboards, charts, KPIs, anything that you can build that has a value based on the data that the system is receiving. So what we aim to do is a system that is really a tool in the hands of the user. And what we see is we have very different types of profiles of people using a platform on the same site. You might have people from operations who want the detail of the values that are read every second, alarms popping up and things like that. And then you might have other teams who want a more global overview, more of a strategic overview of KPIs, and therefore they'll have completely different indicators, dashboards, etc. So that's the first level of what we do with the data that's received on the platform. The second is the control. So process control can be applied to a number of different process units of a water or a wastewater treatment system. A very common one is aeration control, which Katie mentioned before. There are a number of types of tools that we can use to use the data that is received by the system online and then produce an order to the equipment that is being controlled. What we aim to do is, as I said earlier, focus on a process rationale. On that basis, we will define what logic tools we would need to implement to be able to put in place the control philosophy that we've defined. So that may be PIDs, rules, for example, linked to manufacturer recommendations of equipment, and then a number of other tools like fuzzy logic, which we've been using increasingly, and artificial intelligence and machine learning. I'll give a few examples of that in a particular case study. Either way, whatever type of tool is implemented, there will always be one sort of across the board philosophy, which is the point of the game is to try to adjust how you manage that process at every moment in time and adjust to how it's behaving, what incoming loads might be coming in. So it's really trying to tweak it as much as you can in real time, but without having someone having to tweak it physically. It's the system doing it online. So very self-adaptive is the point. Because we really build things on a process rationale, it means we also try to have an overview of the whole site, and we will build in the control any synergies that there might be in the process. So those might be synergies within the site. So for example, on aeration, the air demand and air production side of things, but also using data that's coming from off the site. That might be weather forecast data, useful sometimes to have a bit of an early warning on about incoming loads. It can be power tariffs, a triad, for example, that will also help you give indications on when it may be more expensive or cheaper, and therefore adjust within the leverage that you have, adjust your process accordingly, etc. So, as I said, very very wide applications, and every case is different, every site is different, and every story is different, and then and the objective of each installation is different as well. So you do get a broad range of applications, and this is an example of selection of installations that were carried out on those are on aeration control, and those were mostly sites that had an objective of energy efficiency. So to bring this a little bit more down to earth, I'll detail one particular example, which is the wastewater treatment plant of Lleida. So that's northeast of Spain, rather a large site, so it's almost 90,000 cubic meters per day, so quite a good size site. Switch here to explain the process. So the aeration control, the aeration process that Keely mentioned before here is operated in 2 steps. So you have 2 plug flows for the first step, and then a second stage with 4 plug flows, and then second tanks, and towards final effluent release. This particular site had the consent limits that are indicated here, so carbonaceous, and then a total nitrogen limit of 15, which is fairly usual in a lot of Europe, and then a total phosphorus limit of 1. Phosphorus was only intended to be removed chemically within this design of the site. So initially, when they were starting to look at optimization and process control, they were really only focusing on optimizing from an efficiency point of view, both energy efficiency and chemical usage efficiency. And then what happened is that their consent limit got reduced from 15 to 10. So then there was an added objective, which was to improve treatment performance as much as possible to try and avoid any extension, so essentially capital costs for new build. They really took took it step by step to go through optimizing a number of different areas of the site. So it's quite an interesting site to show, because in one single site I can show several things. It's not to say this is typical of what's done on every site, but it does give you a bit of an overview of what they've done. They started initially simply by producing data, so installing instruments for measuring online in a number of intermediate points of the wastewater treatment plant, and then at the effluent as well. And that was helping them adjust manually some of the set points. And the next stage up was when we started working with them to go towards online advanced control. So I won't explain all of the details of the process control, because, as I said, on this site that there is quite a lot, and it's not the point here. The only importance of this graph is just to show that, as I mentioned before, everything's intertwined. Processes are linked, and therefore the control is also interlinked. So a few highlights of what's been done there. I mentioned earlier the biological stage. The biological treatment is in 2 stages. We're controlling the aeration on both stages, but in very different ways, because they have completely different targets. So the second stage, the 4 plug flow reactors of the second stage, they are focusing mainly on nitrogen removal, and as it's a total nitrogen consent limit, we're looking at nitrifying and denitrifying. What the control does here is adjusting at every moment in time to what is happening in the system, and this is why, instead of having fixed set points, there are variable set points, and you can see here on the dotted green line, it's a variable set point of oxygen, and the green line is the measurement. So this is on one of the 4 aeration lanes. So during nitrification, so aeration, you will have this dynamic oxygen set point, which will depend on a number of online data signals. So we're looking at ammonia, we're looking at nitrate, and we will also look at some criteria that are built with those particular signals, so not just the signal itself, but, for example, a 24-hour average of ammonia, because their consent is 24-hour average. So all of these inputs are inputs to a fuzzy logic matrix that gives us an output, a dynamic oxygen set point for that particular lane. The control also introduces denitrification phases. So that's when you want to create, you stop the aeration, you want to create an anoxic zone to carry out the denitrification process that Keely mentioned before. So the system determines when you can do that, how long that should last, and therefore when should you start aerating again in each particular lane. So it controls all the process from that perspective, from the air demand perspective, and then also from the air production and distribution. It will control the set points of flow of air that need to go into each of the lanes. A pressure set point, here again, all dynamics, instead of having a fixed set point, which is what we tend to see as a baseline situation in many sites. You really try to adjust to work at lower pressures when we can, to be more efficient, and controlling the blowers to have lower running hours of the blowers and working at lower regimes. So that's for the second stage. The first stage of treatment, we're actually looking at very similar data, because it's the same analyzers that we're using. We're reading the ammonia, we're reading the nitrate, but we're using them in a completely different way, because the first stage is focusing on trying to promote biological phosphorus removal on a site that was not designed for that. I won't go into all the nitty-gritty of how that works, but in essence, what we try to do is create times where we're aerating the least possible to create anaerobic zones in that first stage. So virtually the same data, but what is coming out of the control is a completely different philosophy for a completely different purpose on a different part of the site. So that's an overview of the aeration. We also work on the sludge line. So as part of the aeration process, you recirculate part of that concentrated sludge back into and the microorganisms back into the aeration lanes. And here you want to try and have a sludge that is the right amount for the treatment purposes, as well as a sludge that has good settling properties, etc. So here the aim of the game is very different. It's not so much about efficiency in terms of savings, it's more about stability of the system. So we're looking at completely different sets of data, different sensors. So we're looking at level of solids in the aeration lanes, in the recirculation streams, flows treated, etc. But again, using a fuzzy logic tool to have all of these inputs that will then give us an output, which is what flow rate should I make this recirculated sludge pump run at. And lastly, chemical dosing. So on this site, they use ferric chloride for phosphorus removal. As I said, part of the phosphorus removal we try to do biologically as much as we can, but the fine tuning to reach the consent of 1 in total phosphorus is done with this chemical dosing. So initially they had a simple system that was just reading online levels of phosphate, and on the back of that dosing the ferric chloride. So there are 4 dosing points in each of the aeration lanes, and it was dosing the same amount in 4 lanes. We upgraded this by looking at other parameters, for example, not only the phosphate at that moment in time, but also trend and 24-hour averages, because that's in line with their consent. And also really using the synergies between chemical removal and what is happening from a biological perspective, because whether you're aerating or not in those lanes will impact how much phosphate might be how much phosphate might be available in each of the lanes, and therefore it doesn't make sense to dose the same amount in the 4 lanes. It really depends on what's happening in each and every one of them. That's what you can see on the chart on the bottom right there. At the moment that picture was taken, one of the 4 lanes was actually taking half the dose, because that's the one that was expected to have at a higher level of phosphate to have removed. So all in all, with a number of these process control items, they managed to reach that the new level of consent without any new build. So that was actually maybe the best win actually. And then in terms of energy efficiency, 22% savings for energy in the whole aeration process, and then savings in terms of chemical. I've written it there in terms of kilowatt hour and kilograms of chemical. Obviously, there is an impact then environmentally as well. The last layer that they implement on this site, and this module was implemented a year or so ago, is not so much about the process control, it's about the reliability of the data. Because if your control system is using an input which is signals and combinations of signals or calculations that you're going to make on those signals, you need to trust those signals to some extent. And this is what this module does. So IDM stands for Intelligent Data Management. What it does is all of the key signals for that particular process control, it will analyze them using a number of different functions online, and it will then rate it with a percent reliability. If that reliability falls below a certain level, then automatically the system will discard that signal, trigger an alarm, and start using an alternative method, because the output of your control can't be reliable if the input isn't. Now, as one of the alternative signals or values that can be used, one is a soft sensor. So what we call soft sensor, in essence, is a model of the physical instrument, so a digital twin of the physical instrument. So what it does is what you see on the chart on the bottom right there. The blue line is an ammonia analyzer. So this is one of the signals that's used for the system. And at one point in time, and the green line is the model, so it's the soft sensor. It uses machine learning, so it's constantly adjusting that model to try and reproduce what your physical sensor would have measured. So that if the physical sensor fails, and that's what you can see when it goes blank, it freezes to a certain value, then the system discards it and uses the soft sensor instead. Then when the instrument is repaired and goes back online, then you can switch back to using the actual physical instrument. So it gives you that extra level of robustness of the data and therefore of the control system. And that was everything I was planning to explain today. So I hope that was interesting for all, and I'm happy to take any questions.
All right, thank you very much, Lynn. Could I then please ask all of the presenters just to pop their cameras on, and then we can go through a few of the questions that we've gotten. There we go. And yeah, thanks again, all of you, for presenting. Fantastic presentations, really interesting. I'll start off with the ones in the chat here. I have noted a few for myself as well, so we're not going to be lacking on questions. So this first one is for you, Ed. And if you want to see it written, you can just open up the chat as well. So the monitors you've placed in your sewerage system, assume these are similar to those used for short-term flow surveys. Do you have issues with blinding of the flow sensors, therefore giving an error in a step value? And also assume these monitors are battery operated and report to telemetry. How long do the batteries tend to last?
Okay, I'll go through in order then.
Yeah.
I guess a bit similar, I guess, to the flow sensors, but well, of course, we've learned and refined a few after I've been here Wessex a few years. Dad went and rewrote our design standard for how basically took the lessons learned for how to install kit, and we started changing what we did. So we mainly want to balance data quality with maintainability, because if your kit fails, it's difficult to go and get to and to access. You lose all the data. So there's a payoff. What I try and explain is I'd rather have good data from a reliable sensor rather than fantastic data from something that's a pain to get at, because that fails, then you've got to have loads of downtime, so you're lost. But so generally speaking, we've got predominantly ultrasonic sensors, and where possible we mount them close to the surface, so we shouldn't have blinding issues. So yeah, it's not sonic, so things like sonar, radar, chucking a sound wave out, catching it again, and yeah, measuring the depth that way. So it's just a depth sensor we're looking at. In terms of erroneous data, we don't have, when we get bad data back, it might be, sometimes you might have, say, dirt or condensation on the sensor head, clean it off, usually good again. If it's pointing the wrong thing, like for instance, if there's an object it's picking up, that can be difficult. One we're looking at, there's some things we can't get around. Okay, there's for instance, there's a site we're looking at, probably to try a different sensor, but there's a higher level inlet, just blast water, sort of sewage across to the side of the chamber at a higher level. So we just get some noisier data there. It's still usable, but it's in storm harvest, instead of having a nice tight band look at, we've got a wider band of where there's all that noise to deal with. But hopefully that answers some of those questions there. In terms of power source, it's sort of a 50-50 split between mains powered sensors going to a kiosk and mains power come in, and battery powered equipment. So we've got a split where we can use mains power, we do, because it's already sat there and replace battery, and where it's either there's no power source or it's uneconomical to put a power source there, we use the battery powered kit. Let's see, how long to replace the batteries. Nominally they've got a 5-year, well, the warranty's 5 years, but they last longer. So we're at the moment we've got a whole load of new monitors to start doing this first cycle of, we've been through basically first cycle of use, and now we're about to start the first replacement cycle. So that should be starting in April. I think that covered off all those questions.
We do have another one for you as well. Again, on the sensors. So how often are they recalibrated as to assess whether any flow trends are real or just sensor drift?
Yeah, okay. This is I'm hoping that in terms of we do have some periodic alarms tests. So really, because it's not the calibration is also less important, because in terms we don't care about sort of is it 105 millimeters or 115. The only thing that really we care about is the alarm coming at the right point. If there's a discharge happening, is that an overflow happening? Is that real? Is that genuine? And so really what we need to go and do is, by doing periodic alarms tests, we can go say, hey, that's coming at the same level. What I'm hoping we can do within Wessex, now we've got storm harvest, we've got something that goes and says, well, I know what it used to do, has it changed? I'm hoping we can say we don't need to do alarms, we don't need to recalibrate, because we know it's changed, and that can apply for other types of sensors as well, because really with recalibration, what you're trying to do, has it changed? Well, if we've got a system that can tell us that, then that could be a big saving and be a lot better for us. Obviously, there is equipment that is more sensitive that you do have to recalibrate because you're after finer tolerance data, but and you might actually care about the precise outputs, like to feed it into a flow model or something. But yeah, for this, I'm hoping we can try and storm harvest to tell us whether it's the same or different.
Danny.
Great, yeah, makes sense. Keely, one for you. Has the work that you've been doing led to earlier diffuser replacements, or is it better identification of existing required replacements? So is the argument for replacement clear cut, or is there still a bit of balancing to be done of cost versus lower emissions?
Yeah, so the work that I mentioned that was getting done was being done from an energy efficiency reason, so nothing to do with process emissions. And trying to explain, I'll quickly try and explain our AMP process. So I know Ed will definitely know this to be probably bane of his life right now, potentially. So within water companies, we're regulated by Ofwat, and we work in 5-year periods. So we call those AMPs. So we are approaching the end of AMP 7 and coming into AMP 8. So we are in the sort of, well, we're past it now, but we're in the planning stage. So in order to plan for next AMP, knowing that process emissions and net zero is going to be one of the things we wanted to focus on, we used a multi-capital approach to ensure that we met the reduction targets in a cost-effective way. So our OPEX, CAPEX, so capital expenditure, operational expenditure, but also having that carbon benefit. So we won't be doing anything in relation to diffusers until next AMP, and that is assuming that we get that funding from Ofwat. So hopefully in the next year or two, we'll be able to find out if we will be getting that. And I'm just double checking I've answered that question. So yeah, it'll be a mixture of both, but in next AMP, it'll be primarily focused on that carbon benefit rather than a solely cost benefit.
Great. can't see any questions for yourself, Lynn, but I do have some. So I hope you don't mind me asking. So where you've been to a site, you've implemented your control system, it's running fine, taking aeration as an example here. So let's say you're controlling on, you've got a plug flow reactor and you've only got a single DO sensor per lane of per plug flow reactor, and that's what you're sort of controlling using that. How open is it to add additional instrumentation into that system? So you wanted one at the start, one in the middle, one at the end, for example, and maybe control either an average or a zone type control.
Good point. Yeah, I went very fast on the instrumentation side. So the process of how we put together a solution and implement is, first of all, we try to understand what that particular site is like. So are they plug flows, are they oxidation ditches, etc. Type of configuration, how many, type of air production systems, are they blowers, are they surface aerators, what's the consent limit, are they hitting the consent, or are there issues? So a general understanding of the site, understanding the focus. So is it a case of reducing energy? Is it a case of reducing process emissions? Is it treatment performance, etc.? And we'll also look at what existing instrumentation is available on site. Typically, we'll see that they tend to be 1 or 2 DO sensors per aeration lane. That's a usual standard. Sometimes some redox, and sometimes on site that have nitrogen consent, there'll be some ammonia and maybe nitrate, but mostly oxygen redox tends to be the standard. So based on the control philosophy that we would suggest for each given case, then if the instrumentation that we would require to be able to implement that control philosophy isn't existing, we will suggest to implement that. We as Createch are not instrumentation manufacturers, so we'll only suggest what we think is relevant, and happy to supply or to give recommendations on types of instrumentation. But yeah, it's always linked to whether it's relevant or not for a particular control philosophy.
Okay, but if you've already got the control going and you ascertain that there was enough instrumentation already on site, but either local operations team or whoever decided that to add additional DO sensors so that you could maybe see where along that plug flow reactor, for example, you're achieving treatment and how far along, that sort of thing. Is it fairly easy to add that in, so retrospectively change the models that you've already created?
Oh yes, absolutely. They're very evolutive models, and actually the particular example I showed of the ADA is the case where on a single platform they really went through optimization on different parts of the site, also little by little, and so modules and extensions have been added on. And on the aeration side of things, for example, when we started early on, they had a consent limit of 15, then it got changed to 10, so that led to modifications. I think they changed the blowers as well at some point, or something like that. And so, yeah, modifications can be done at a later stage. Absolutely, it's all done in house, so we can easily modify and adjust.
Okay, great. Ed has a question here, adding on to that, where you're requiring additional instrumentation for to implement your solution. Are you seeing that having a big impact on things like maintenance and basically how much attention that site needs from the local operations team?
Absolutely. As a general rule, I'd say the more the instrumentation, the more the maintenance associated. Now, different types of instruments will require different types of attention as well. And also, for example, for ammonia, whether they're ISE type instruments or whether they're analyzed type instruments, it's a very different story, the type of attention you need to give it. And the first might be more sort of on-site work and a more recurrent work, whereas where it's analyzers, it might be easier to sort of get the manufacturer to come and do that. So it's not necessarily the same way and the same type of attention, and that's actually something we tend to take into account when we give recommendations where we need additional instrumentation for a site. We'll usually try and understand how maintenance procedures are carried out on that particular application to be able to recommend one or another type of instrument as well. But that is also where the last item I mentioned comes in as well. Having that extra layer of robustness where you're constantly looking at how reliable your signals are does help you gain a bit of time so that you're not completely lost if you've lost a signal.
Okay, great. And I guess next one I have for Keely. You mentioned obviously low dissolved oxygen levels being being an indicator of high risk of increased nitrous oxide production. Do you see the opposite as well? So over aeration being a big issue, or can we all just ramp our blowers up and solve the problem?
No, please don't ramp blowers up. One, from an energy point of view, and also, yeah, so you get that strip-in effect where you're giving it too much oxygen, and it'll also create N2O. So it's sort of getting the sweet spot, and you have to almost treat each site by site. That's what we've been finding. So even though we've looked at 3 conventional activated sludge plants, which on paper should be the exact same process, they're not. As I mentioned, it could be loading issues. It could be, so for example, one of ours is an anaerobic digestion site. So whatever's coming in that influent water is going to impact the process differently. So you need to sort of treat them all individually rather than standard across the board. So yeah, and you can almost give a generic sweet spot of where you're looking, but once again, that can be based on the site. So, you know, I could tell you, 0.7 for one site, but it could be 1 for another site, or 1.2. So it's all site by site basis is what we're sort of finding at the moment.
So in order to effectively measure and hopefully hope to mitigate the production of nitrous oxide, then site-by-site monitoring will be required, is what you're saying.
Essentially, or obviously technology is heading towards those predictive models, which is also, yeah, what we're doing with cobalt water, for example, which we're finding to be really beneficial because it brings that cost down and that intensive monitoring bit. Because as you just mentioned yourself, you have to have all those different instruments inside coinciding with it. So DO, ammonia, mixed liquors. So if you can use predictive models, then yeah, that's what we're finding to be the best.
Oh, great. Just so cover all the bases, and Ed, I've got a few questions for you. Yeah. So obviously, as part of the Storm Harvester, well, it seems to be more than a trial at this point. It seems to be successfully working. You're collecting a lot of data. Do you find that is this data being used for any other business efforts, or, for example, identifying high infiltration areas, or yeah, anything like that?
Yeah, we're starting to. It was quite interesting because the back end of the year was so wet, as everyone who lives in this country will be aware. It was quite soggy in November and December. It didn't really stop raining. Yeah, what that meant is because the models were trained on 2 years worth of data. I guess that also the previous year was actually quite a drier winter. Also, funny enough, you know, it's wetter over. You split the year in 2, basically dry months and wet months. By the way, you know, the winter was drier like the previous year, and so we've trained. Some of the training has been on drier data. So when we then had a really wet year, actually it's not broken the models, but then actually it's more of the sites have gone outside expected, have gone into the unexpected behaviour and have been flagged up. So at the Wessex region, I didn't explain at the start, but you know we've got Somerset and Wiltshire and sort of and Bristol as part of South Gloss and Somerset too. But Somerset levels, it's reclaimed land. You know, lots of our pumping stations there and likewise the chalk regions in Wiltshire, they just went high. And they stayed high and they stayed in alert for a long time. And what we're going to do within Storm Harvester is probably from after Easter, we're going to look at those with them and retrain our models. We're really looking at ways we can go and deal with that. That's the same as applying for other water companies as well, you know, because it's been wet for everyone, I think, and so that's affected us all. But part of this is then we do need to make some judgment call about, you know, actually there's some sites that just went really high and stayed high because there's so much flowing in. There's other sites, but we don't, and so we want to retrain to take account of that. What we don't want to do is mark bad infiltration sites where we're going getting groundwater entry into our pipes and entry into our systems. We don't want to accept that as being normal because we still want to highlight that as being bad. So that there is, it does need to be handled with caution, and we've obviously seen a lot going on this winter, and there's also discussions internally, and we were going back to Storm House with more proposals about actually can you do this and that, looking at more stuff with groundwater for us. So we've bought into the system, and we're trying to see how much value we can go and get out of it. So, but we're at the start of that process really, because we're still adding more sites at the moment, and we're just learning what it can do. And I've described it previously a bit like, so if you think about sort of telescopes, at the time I thought the analogy they put that new James Webb up in space, you know, but you go back out with a telescope, you can see a bit, you know, with your eyes you can see the moon. You put a telescope, you can see it more clearly. Get a space telescope, you start seeing all the pretty pictures, all the gas clouds, and all the rest of it. But the point is, you still look at the same things, but you look at more detail. And that's sort of the process we're going through at the moment. The fact that, well, we still look at the same sewers and the same sites and the same pumping stations, but now we've got better resolution, or we're having our attention directed at the most significant problems rather than getting lost in a whole sea of data, really. So ask me again in a couple of years what we've done differently, because we'll have made better use of the data then and explored some more avenues.
Okay. Yeah. There's a bit of a follow-up question here from Lynn. Once system's installed for a site, how long does it take for the system to be calibrated and operational on that point? Or is there a learning phase for additional sites coming on?
There's I said originally we were giving them 2 years worth of data, but that's because, you know, actually we had sites that have been active for a long time, and I know originally when Storm Harvest would look at things, they said, look, really after 2 years there's little benefit. However, it can be brought in. I mean, I think somewhere between 1 and 3 months is the least you really want to do. So there's so in terms of retraining, so there have been some sites recently where there are some original installations and they've been changed by sort of just because they've been revisited after 5 years. You know, so if Keely was explaining about the AMP process, exactly that. They wrote AMP 5 ones, now we revisit them again. So somewhere between 1 and 3 months, and of course it is affected by what happens in that training period. If we trained it on a really dry period and then got really wet, it's probably going to struggle. So there's still some learning there, but Storm Harvester at one point a year ago they're saying really, but no, you know, don't get less than 3, and then at times said, well, maybe 2 or maybe 6 weeks or maybe 4, but you know, the longer the better, but we haven't always got that option.
Okay. Great. And this, also for Ed, have you looked to incorporate any additional data into Storm Harvest, or is that something that it can do? So, for example, looking at how often the pumps are running, for example, or if they're running continuous or not running when they're expected to run.
Yeah, so certainly, actually, Northumbrian, I think, Water, I think the first company that started doing things with Storm Harvester, and they were originally looking at sort of pumping station, pump run stop. So it has the capability that we have given Storm Harvester some pump data, but we've not started using it in earnest. And there's another proposal in at the moment to go. Potentially might take them up and pursue that a bit further, but also we have our own in-house tool, so it's there and it's available. And our grand picture, in an ideal world, what we really want to go and have is have some form of platform where we can plug in, we can feed in, we have all our data, we feed that data into a whole load of other programs that get hosted by, you know, one program to go look at. This is all our analytical platform. Look here, rather than looking at 10, 8, whatever different screens. If that can just have everything plugged in and put into one nice dashboard, then it doesn't really matter where that data's come from. And likewise, you know, if one fails, we can put another one online. So we're again, we're exploring that at the moment, but we also do things like that using some in-house work to look at pump run stops and you know, are the pumps running for longer than they should have been? Is the pump output correct? You know, I mentioned the burst detection. You know, actually, so if we put this much water in sewage into a pipe, does this much come out?
Burst detection stuff is that's the one where you've been adding pressure sensors along various parts of your network as well, isn't it?
Yes, and that's continuing. That's been very successful for us actually. Although Technog told me today that sort of over in Welsh you've got testing out some fancy sensors you're pleased with, so we'll ask them about that.
Okay, great. Not seeing any further questions coming in. So I'll just use this last few minutes to plug the guild a little bit more. So let me just present. Well, so there we go. So thank you all speakers for your presentations. And yeah, as I said, I just want to give a little notice to a couple of upcoming events for the professional development network side of our guild. So that's for developing professionals, so under the age of 35 is normally what we say in that. So we have a couple of paper competitions running that still have upcoming deadlines. So that's the Scottish branch one and the All Ireland one as well. There are 2 branches in Ireland, obviously, but they're combining theirs for this year's competition. And there's also always events running. So if you're interested in further events, we've got there's just to look at the Guild's events site. And yeah, I think I'm happy to call it there unless there are no further questions. Well, thanks everyone for joining today. It's a really great turnout, and thanks to the speakers once again. Thanks for your time. All right.
Thank you.
Thanks everyone.
Thanks everyone. Bye.
Thanks, have a nice end of your day.
Bye.